Welcome to AI for Good, the leading action-oriented global and inclusive United Nations platform on AI. Organized by ITU in partnership with 40 UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end, as we will hold a 30-minute networking session in the neural network. Here you can meet, ask questions to our distinguished speakers, connect, and chat with the AI for Good community. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello everyone, welcome to today's session on Spatial Digital Twins and AI, Racing into the Future. I am Harsha Madiraju, Associate Director at the World Geospatial Industry Council. Thanks to the International Telecommunication Union team for providing us with the AI for Good platform. Through this platform, we are bringing the geospatial community closer to the tech and global development communities. On AI for Good platform, we are having dialogues and discussions on artificial intelligence and its integration with Earth observations and geospatial technologies. I thank all the attendees for joining the session on behalf of the curators of the AI for Good Geo AI Discovery Series. Nadine Alama from Open Geospatial Consortium, Maria Brovelli from UNGGM Academic Network, and Barbara Ryan from the World Geospatial Industry Council. Now, on to the topic for today's event. Recent advances in technology and reduction in costs of sensors for data collection have created an interest in a breadth of digital twin use cases. Now, we see digital twin applications moving from the factory floors to our streets and cities. In this context, spatial digital twins are those digital twin projects that have two additional specs. One, spatial positioning, and two, dimensional accuracy. A report from my organization, the World Geospatial Industry Council, has found that spatial data integration is crucial in adoption and scalability of digital twins across 25+ use cases. I'll be happy to share the download link of this report in the chat window in some time. Further, according to this report, the broader adoption of digital twins across various use cases requires more accurate spatial information to align the digital and physical worlds. WGIC also presented a future vision as part of this report, and we see some fantastic possibilities with digital twins into the future. Further, in this report, we said that digital twins will evolve in 3 scales. 1, micro for site-specific applications. 2, hybrid twins at city scale. And 3, macro twins at country, regional, and global levels. This creation of digital twins across various voxels is not an easy task. Creating a near real-time digital replica of the physical world will require a continuous update through numerous data sources and sensor feeds. Data uploaded from field to cloud-based platforms assisted by automation and AI is seen as a way forward to provide faster access to data and insights. Some key capabilities now exist in the geospatial sector just to do that. We now know how to process large volumes of satellite, aerial, and LiDAR data sets and integrate with AI, bringing life to digital twins. In this session, we have a fantastic lineup of speakers who will talk to us today on such capabilities and use cases from their individual organizations. For sure, these will generate a lot of curiosity and we'll have a lot of questions to ask. Please share your questions with us in the chat window and we'll try our best to answer all of them at the end of the presentations, where we'll have a 30-minute Q&A and panel discussion. After the panel, please don't forget to join a 20-minute networking session hosted on the AI for Good neural network, where you will have additional opportunity to talk to the panelists and attendees and build new connections. Without further ado, I will introduce the speakers for today, and I will invite them to turn on their cameras for this introduction. The 5 experts we have with us today are Dr. Nick Hanowski, Department Head, Ground Segments and Operations, European Space Agency. Nick, if you can turn on your screen, on your camera. Dr. Uwe Joschnock, Director at Hexagon Safety Infrastructure and Geospatial. Chris Tanner, Business Development Specialist at AAM. Omar Maher, Director for AI at ESRI. Peter Atala, Founder and CEO of Voxel Maps. We are all glad to have all of you, and we thank you for agreeing to spend your time with us today, to spend time with the community, to educate the community about this topic of AI and spatial digital twins. A special announcement. I am also pleased to let you know that the speakers from the private sector companies that you see today are from WGIC member companies. If you are a geospatial company and want to join WGIC, please talk to me. Before we start the presentations, I would like to remind our guests to be on time, as we want to have a good time spent on Q&A and panel. With your permission, we'll keep the time for you. And now, we'll all stop our cameras and mute ourselves to have the first speaker, Dr. Nick Hanowski from European Space Agency, presenting for us. The stage is yours, Dr. Hanowski.
Yeah, thank you very much, and good afternoon, ladies and gentlemen. It's my pleasure to start this round of introduction on the topic of digital twins and artificial intelligence. I'm waiting till the presentation is loading. Here it is. And I would like to take you on a 7-minute journey about of the considerations that we at the European Space Agency, from an Earth observation perspective, are bringing to this topic. So with the first slide, let me just show you, next one, please, the fleet of Earth observation satellites that ESA has developed in cooperation also with the European Union, which forms the backbone and the actual data assets and data sources that have led us into the consideration of digital twin applications and digital twin artificial intelligence usage. To give you a feeling about the data volumes in Earth observation, just from this system, we are disseminating every day about 0.5 petabyte of data. And of course, with such data volumes and with an expanding satellite fleet, the question of how to integrate this data into a more usable and applicable format has arisen. Next slide, please. The next slide shows you the so-called what-if considerations that have led us to ponder the potential of digital twins. So what if we would be able to create a comprehensive digital replica of the Earth to simulate and observe Earth-human interaction with high accuracy? If we would be able to harness innovative extreme-scale computing, data handling, and AI technologies to continuously update Earth observation data and other data that is being fed into the twin, and enable accurate Earth system simulation and prediction capabilities. Ultimately to provide detailed views of past, current, and future physical changes. And the emphasis is here that in addition to what we have been doing in meteorology and in climate evolution, we would like to expand the predictive potential of Earth observation data into many, many other domains, transforming data into information for general decision and policy making. This is the ultimate objective that we are pursuing with this digital twin of the Earth approach that I'm outlining here. Next slide, please. So what are the key components of a digital twin Earth system as it's being developed? First of all, a cloud infrastructure in order to handle the standard processing and the data storage aspects that are required. The HPC infrastructure in order to support the simulation and modeling aspect, harmonized data lakes with the corresponding interfaces to utilize very different data sets. The competence of Earth simulation observation centers, which are focusing on the modeling and the algorithms that are supporting the modeling and simulation efforts. The AI and software and science competence underlying the processing that is required in order to come up with the ultimate functionalities of such a digital twin. And of course, we need the European data networks in order to supply the data, but also ultimately also the information to the relevant entities that can utilize them for the policy making that I've addressed in the slide before. So in the end, simulation monitoring for past, present, and future aspects of the Earth system, with a strong emphasis on the visualization of the system and the ability for non-Earth observation specialist users to utilize such a system. Next slide, please. So some of the key components and some of the key principles that we see in the implementation applied is the interaction of various elements, the data management element, the elements of functionality for the twin that I've just described, and the actual digital twins, which are in preparation, thematically strongly focusing on things such as extreme events, climate change adaptation, and the ocean environment. And we want to be able to display results from the first year of implementation of the system, large user communities, hopefully attracted to the system within 3 years, to be open, to be evolutionary, to be interactive, and to generally generate the visibility that such a system thrives on in terms of usability and functionalities. Next slide, please. So one key initiative has already been kicked off on behalf of the European Commission, who is leading the Destination Earth initiative. The European Space Agency, the European Center for Medium-Range Weather Forecast, and the European Meteorological Satellite Center have together started to implement an architecture with the corresponding infrastructure and software developments to integrate and coordinate European industry and member states' assets in order to realize a system that is particularly focused on these aspects of supporting European Union policies, for example, in the context of the Green Deal, with climate change adaptation at one of the core elements, and extreme events as another element of current policy urgency. Next slide, please. And this already brings me to my last slide, just to show you that on the ESA side, on the European Space Agency side, we are also working on thematically constraining further digital twins in order to support up to a pre-operational status additional digital twins that are emerging in the European context. Thematically, we have systematically looked at forestry, hydrology, the Antarctic environment, food security, and similar issues. And my very final slide, next one, please, is showing an example out of these preliminary digital twin instantiations that we have established, a digital twin for Antarctica, which is particularly applicable in the context of the dynamics of the Antarctic ice sheet and the various cycles that are relevant for the overall ecosystem of the Antarctic continent here. So that's a quick rush through introduction. So I think I've stayed within my 7 minutes, and I hope for animated discussion later on. Thank you very much.
Thank you, Dr. Hanowski, for a fantastic talk on the valuable work from ESA. We now have the second speaker, Dr. Uwe Jasnock from Hexagon Safety, Infrastructure and Geospatial. Welcome, Dr. Jasnock.
Thank you very much for the introduction, Harsha. We are now going to lower the altitude a little bit. So from satellite, we are now going to airborne and street or track-bound digital reality scanning. And I'm going to talk a little bit about how we can accelerate the generation and the usage of digital twins by a higher degree of automation. Why it's so important, I think there's no doubt that urban digital twins will change really the way cities are planning and operate their future. And what you're going to see there is not a video per se from a drone or from any kind of airborne vehicle. In this case, it's a super mesh, fully automatically generated by airborne as well as street side data capturing. And here the key is really that this model is completely and fully automated generated. Now, the point behind this that a digital twin should be definitely more than a pretty picture of the reality. We need to create insights, and these insights will be generated when we are able to create objects on that digital twin or within the digital twin by identifying structures. And we have to do this either on visuals, on imagery, or with point clouds. And both identifications of these structures and objects is achieved by AI-based semantic evaluation. I'm here showing a little bit of the process on products on what we are generating. So out of the airborne pictures, we're going to create true orthophotos. And with the help of AI, we are generating a land cover, means land usage. So in red, you're going to see for example, buildings. In yellow, black, you're going to see infrastructure. In gray, you're going to see some gray space and streets. We have more than 25 classes where we're going to detect in these pictures. And the detection process ends up in a probability map for each class. That means that within the detection, we're going to filter out with the help of the probability map for a specific class, for a specific challenge. And second step, in a post-processing step, will be then, for example, creating vector objects. And here, in this case, this will be a tree cluster. Now, why it's so important to utilize these AI-detected semantics? First of all, the detection process itself in the raw data creates multiple data products like a super mesh, as we have seen for the city of Munich. It's an LOD2 city model. We do get the tree catastrophe and we detect the infrastructure. But based on that, we can generate derived solutions. For example, green-gray space per parcel, which is very important when you do have heavy rain. How much will be going into the sewage and drainage system? We have, when we go with our hexagon sensors, we do have hybrid sensors where we automatically also generate a very fine-grained digital surface model, which then sets the basis for heavy rain analytics. So where's the water flowing to? And also, and this is kind of indicated in the next video, it's used for protecting critical infrastructure in storm events. For example, if you do have, in this case, the infrastructure is a rail infrastructure, and you see here the different catapults, and here's the different products. When you have the trees and you're going to simulate the wind event, you're going to see which part of the infrastructure, especially in the power lines above, you're going to see how they are affected and where you're going to expect some dropouts in schedule because the power went away. Now, linking the urban digital twin to the next one, it's really a digital twin for infrastructure, in this case, a rail infrastructure. And here, again, the digital twin is really a key concept. And in this case, for the infrastructure, it's really to improve the future rail operations, because rail infrastructure is a very limited resource. You need to optimize it to all different dimensions for an optimal usage. Now, what we have done here, I'm going to show you here, is a digital twin, which consists out of a couple of different point clouds. Exactly, we have captured a point cloud from the rail, from track side. With a partner, we got capturing from the roadside, and also for a specific bridge inside, we're having also data capturing from a UAV. And then we can interact with that point cloud, like measuring in these things. And then the next more important step is really detecting objects of interest in these point clouds, because the detecting objects in point clouds is a different AI mechanism than detecting and cataloging and categorizing objects in imagery. And this needs to merge together and fit together. And what we have done then is link those objects to the digital asset management of that track. And then you can really start a lot of process optimizations like the asset management update, change detection processes, and. And This video actually shows how you're going to work in this point cloud in the browser. So basically we have here now displaying two different point clouds, the one from the track side and the one from the street side. And for example, here we're going to measure the height of that bridge, which is of course highly important. But unfortunately, this is not AI based, it's just classical measurement, so nothing really specific. More interesting, it's here with this bridge. And I want to draw your attention to these green poles, because all these green poles are automatically identified by semantic segmentation in the point cloud to a certain class. In this case, these are the quaternary poles. And each of these poles is an intelligent object. Meanwhile, as we have linked these detected objects with the asset management, so we can really go and provide more information. And this more simplified view, these are all objects we are detecting automatically by AI in that data set, like the platforms and the noise protection walls and these different poles for all different pieces. So this is a really important step when you're going to move these things together. Now, the last sample where we bring the urban digital twin together with infrastructure is for public ground transportation, where we're going to fuse data from a super mesh. In this case, it's the city of Frankfurt, and fuse that data with the asset and the infrastructure information from our public ground transportation provider. And we really generate here new 3D spatial dependencies. We are going to include also BIM information, because building information management for infrastructure is going to define the assets of the future. And therefore, it's really important to us to understand these assets. And what we are going to show you here is for this specific part of the city of Frankfurt. In orange, these are the trams, and in blue, these are the subways. Of course, we are lifting the subways to upper level, because otherwise you can't see them very well. And we are now displaying all the stops and entry point and exit points. And this is, again, a fully intelligent model. So we're going to select one of these points, and then we can start workflows and interacting with the asset information in all different kinds. And just give them a short second for interacting it. So you're going to see here now some of these workflow masks where you are guided through that data. Now, for Hexagon, we truly believe that a digital twin is really generating new insights and breaking up silos if we're going to overcome the situation of a static pretty picture, so that we're really starting to generating and identifying intelligent objects inside this digital twin. However, we also truly believe that the digital twin it's not a fixed product. It's like a journey based on different platforms with different use cases, which then generate the outcome to the customers. And it's really based on teamwork of between the customer and the provider. So it's not a single product like any kind of typewriter supplements like a Word or something like that. And by that, I'm staying hopefully in my 7 minutes. And so my question to you is, what is your plan of A, utilizing a digital twin, and B, utilizing artificial intelligence inside this digital twin? Thanks a lot.
Thank you, Dr. Jasnak, for bringing this technology perspective from Hexagon. The end questions are really the ones we want to bring to the panel and have a more discussion around it. Thank you. We'll now move to the third speaker for today, Chris Tanner from AM. He's joining us from South Africa. Welcome, Chris.
Good afternoon. Thank you for that introduction. So I'm from AAM. We're an international geospatial company, part of the Wilpert Group, and we provide a full spectrum of geo solutions using aerial acquisition, mostly imagery and LiDAR, point clouds being the main sort of data sets that we work with. And we use these to create rich spatial digital twins, mostly of cities. We refer to them the digital twin of the built environment, and we've done many projects in the city space with these projects. So I'd like to give some background on how we build these 3D models of the digital twin, and then where machine learning and AI have a place, and where are they used to improve and build the model, not only build the model, but how we use some AI and machine learning in our internal data production processes, which has been very, very useful. So if I move on and have a look at what we mean by the smart city. Now, smart city means different things to different people, but we'd like to think that we support the smart city thinking, and of course also the supporting the sustainable development goals that the UN has put out there. And if we look at what smart cities cover, there's many areas that they cover. And if we look at things like smart mobility, for example, transportation, which then leads to autonomous vehicles which are coming, and where would they fit, how they're going to work. Smart communications, if we think of 5G transmission between buildings, inside buildings, between the buildings, the smart city planning, the smart energy, which may be looking at solar panels on roofs. All of these things are happening, but what's relevant is that they're all happening in this 3D space. Even this graphic is highlighting the buildings that this all operates in. So the digital twin has to be a 3D solution. And as much as it's about the buildings, it's also about many other aspects which are also in 3D, which can include roads and utilities and other infrastructure, but it's by far and large the buildings that dominate. The focus is also on the high resolution and the high definition that we work at. So we call it HD 3D. So we are dealing with this high resolution, but which also means very large data sets, either as imagery data sets or point cloud data sets. So to give an example of what that looks like, a typical project where we've done 3D city modeling, building modeling of big city areas. And as I said, the building tends to dominate here, but there's many use cases that go around these. They're mostly the visual use case, but also many of analytical use cases. And we tend to have to work with these levels of detail. So this is what we term level of detail, from LOD 0 right up to LOD 3. On the right-hand side, you're seeing probably the level of detail in LOD 3, which is really every part of the building, every piece of detail. They all according to the standards. These are City GML version 3 being the newest set of standards that we work towards. So this gives some idea of how we do these buildings. So the real question then is, how do we build these, and what is the value? So not only the geometry value, but also the textures that are applied to these buildings. So you get all the use cases can be used with either with the visual content or the analytical content. The textures, interestingly enough, give opportunities for other avenues of AI, which is like determining materials and finding doors and windows examples. So much more avenues of getting it from the texturing and not necessarily from the geometry. So this then raises the question: where do we use it? What is the role of AI? So when we look at the work, the 2D footprint is the most obvious example of where we use machine learning. I say this is the easy part because it is quite a mature methodology now, and it is easy. Except on the right-hand side, you do sometimes get buildings that are not segmented properly, and on the bottom right-hand side, the case where you have vegetation covering the building and all that has to be solved. But as I said, this is very mature at the moment, and that's really where we start. Moving on from that, we have examples now where we can use machine learning to get out the higher detail, the level of detail too. So on the left, you can see those are oblique images. In the center is the vertical imagery, and then on the right-hand side are the models that have been generated, where they now add an LOD2 level of detail 2, where you are actually seeing the roof structures and much more detail in that building. So this is where we are at the moment with our research, with the work that we do internally in the company, and with select partners who are very good at this and who've refined these methods. I'll just move quickly now to another area totally, which is where we use aerial LiDAR, which are dense point clouds that we capture from the air. And internally, we have to process these. So we've actually developed a single web portal to do this, application portal called LiDARnetics, where we've actually used a process of mostly automation, but definitely some AI and machine learning in the process, which has really helped tremendously with our production work, our internal production work, and the workflows. So from the upload through automated processing, through AI and machine learning, and then to deliverable. We've used it and set it up with multiple components. It's evolved over the last couple of years, based largely on AWS, but that's really a historical situation. But now really got to a situation where we're getting huge benefits out of this with the processing of the LiDAR projects, the benefits of cloud computing, the benefits of scaling vertically and horizontal scaling on the processing, where we can spin up instances hundreds at a time, thousands at a time if we need to, depending on the project. The machine learning and the smart part is coming from doing the classification, automated classification of ground and non-ground points. That's giving us good results. We're now going to move that on to do finding classification, applying it to classification of other feature classes of buildings or vegetation and other things. So in summary, it's a brief summary. So AI has a huge role to play in this work that we're doing around the smart cities. We can produce data quicker and faster, better products, and really extract, the vast content of information that exists in the imagery and in LiDAR data sets, all in support of smart cities and the Sustainable Development Goals. So I'd like to end there. Thank you. My details are on the screen if you need to contact me for anything. Thank you.
Chris, it is a great pleasure to have the perspectives from AAM. Thank you very much for joining us. We now have the privilege to have our fourth speaker, Omar Maher from ESRI. Omar, the floor is yours.
Thanks, Asha. Let me share my screen. And I hope you guys can see my screen now. Perfect.
Yes.
A lot of talk today about AI, machine learning, very important topics. What I would like to cover with you guys today is the following. I would like to spot the light on two things. How can data science practitioners easily build machine learning models that can achieve those different workflows that you have seen today? And specifically, how can they do this easily, right? How can this technology be accessible to the greater good of technical or non-technical people? So first, just to set the stage, we look at AI as the big idea of achieving human-level intelligence. And usually when people talk about AI today, it's usually about machine learning one field of AI that's about learning from data to derive rules and extract patterns instead of being explicitly programmed. And deep learning as one type of machine learning using something called deep neural networks, which is becoming recently very good at handling unstructured data, highly dimensional data like voice, image. So in the context of feature extraction, object detection from different kinds of imagery and LiDAR, what we're talking about is mostly deep learning today. And this is a typical machine learning life cycle, right? So in order to derive these beautiful information products my colleagues have shown, usually you need to go through these steps, right? You get the data, you prepare it, you train a model to do something, let's say detecting building footprints, and then you use that model, that's called inferencing. And then the world doesn't stop here, right? You derive insights, you do some level of analysis, you build some information products, and you start sharing it. So I guess it's very important to stress on the importance of being able to do this kind of process end-to-end easily, right? Because it's usually a very iterative process in nature. These are some examples for the kind of some digital twin automation pipelines that we have worked on in Esri. So detecting damaged structures after hurricanes, or doing building footprints at scale, land cover, pipeline encroachment, palm trees, roads, oil pads, road cracks, swimming pools, you name it. And this can also be applied to LiDAR, as my colleagues mentioned, right? So we have been working on detecting utility poles on lines, encroachment, trail assets, buildings. Now, with these two, I would like to highlight two things. How can we make this easier? One way of making that easier is to enable the end-to-end process. So in ArcGIS, Esri's flagship product today, we enable the end-to-end deep learning process, starting from imagery management, labeling data to generate the needed examples to train a model, training a model. All of this, by the way, happens with a button click, and you can do it through Python interface easily in a couple of lines of code. And then inferencing, analysis, and field monitoring. Now, one way of making this really easy and enabling better access to it is the idea of pre-trained models. So in Esri, we have developed many deep learning models that have been trained on large data sets. Those are mostly plug and play. You can download any of these models today and use it in your software, ArcGIS. So you can see classical things like building footprints and land cover mapping, but then you're gonna see more advanced things like tree-point cloud classification from LiDAR, or global road extraction, or power line classification, right? You can see things like shipwreck detection from bathymetric data, solar panel detection, etc. So I wanted to stress a little on these and maybe show you some examples for these models. This is the output from running, for example, the building footprint model. As you can see, it's pretty neat, right? And this is available in different flavors. It's available globally. We have a model for Africa, for example, because buildings tend to differ based on geography. So there is a model for Africa. There is another model for Australia, for example, here, as you can see. And all of these have been trained on large amounts of data. Another interesting story I've been working on is road extraction. So the idea of taking an input, let's say for a nation or a country or a whole city, and digitizing all of that in a single click. Let's actually refresh that. So while it's loading, maybe I can show you another interesting example of applying this technology. This is, for example, detecting vessels from synthetic aperture radar. This is some work we've been doing in the utility space, where we're interested in detecting vegetation encroachment. So you can see here we have models for detecting buildings, utility assets like poles, and encroachments. So the boxes in red represents trees that are in high proximity to the utility lines, which might indicate a risk, and hence we can automate that whole workflow. Let's see, for example, here we have some of those trees here, and then you can do this at scale for an entire city in 1 or 2 hours, for example, versus weeks, right? And the same thing could be done with 3D. This is a raw 3D point cloud collected for a major city in Australia. And what we would like to do is to quickly assess the vegetation risk, right? So we run 2 pre-trained deep learning models, one for detecting utility lines, power lines, which you can see here in the turquoise, and the trees, and using some other techniques to detect the ground and buildings. So we arrive to something like that. And we're doing this on a city scale, right? So that's the idea of automating digital twin creation, is how we can do this on major extents at scale. And then you can leverage spatial analytics on top of that to assess the risk. So for example, yellow represents the trees below the power lines, which is a bit risky. And then orange represents the trees above the power lines. And then red represents, when they are intertwined like that. So as you can see, different types of analytics to enable risk assessment. Let's see. This whole scene has been like end-to-end fully automated the generation of 3D buildings with complex roof types. It's using 2 types of deep learning, one for detecting the building footprints, one for predicting the roof type. And as you can see, it's been done to scale in almost 30 minutes versus weeks. This one is for damage assessment. So after fires, you can quickly assess damage. Where are the buildings damaged versus where they are not? And examples are endless. So what I would like to encourage you to pursue is to have a look at the pre-trained models and really start doing that today, right? That's the objective, is to make it easily accessible. With that said, I would like to thank you again, and moving forward to my next colleague. Thanks.
Thank you, Omar, for presenting how AI tech from ISRI is helping us create spatial digital twins. The final speaker for today is Peter Atala from Voxel Maps. Peter, great to have you with us today. I welcome you for your talk.
Thank you very much, Marshall. Let me just share my screen here. Good morning, everybody. I'm based in San Francisco, so it's morning, but I appreciate people are tuning in from all over the world. Really great talks from everybody else, so I think we're going to have a really interesting discussion. Today, I want to talk a little bit about what we're doing at Voxel Maps, really around building digital twins that are persistent, which means they're always on, they're real time, but can also change in time. So how can they evolve to create a model of the planet? So everything we do at Voxel Maps is really around this concept of building maps for machines. So I'll just take a moment to explain what I mean by that. So human maps we're all familiar with. These are the maps that we use in our mobile phones, on our computers, in our cars. And really they're around 2 use cases. One, to navigate people to an address. The second, to kind of display geodata. There's some kind of data layer on top. The majority of human map data is 2D. There are some 3D elements, but it's not extensive yet. And it's pretty low resolution. We're talking 1 to 3 meters typically. When we're looking at a machine map, this is actually very different. So firstly, we're talking about true 3D spatial models. So we're actually looking to analyze everything, not just the big objects like the buildings and the roads, but also infrastructure, telecoms, utilities, and then in non-urban environments, vegetation and land structures. We do this at a really high resolution, so 1 to 4 centimeters is typical. And so at that kind of resolution, it's not just about the location of objects, but also about the measurements, the attributes, pulling back features from those objects and insight as well. So when we talk about machines, that's everything from artificial intelligent models to better understand a city or a given environment, through to forms of autonomy, like autonomous vehicles, robots, drones. And so while the initial use case is typically outdoor, we're really looking holistically at how would you actually create a twin of the entire planet, everything. So that includes indoor data, subterranean data, even ocean data as well. So the approach that we take is a volumetric approach, and that's a little bit different from traditional 3D. So we've seen some really great examples of 3D today from the other speakers. And this is an example from Google. It's a great human visualization tool. It really is 3D, and there's lots of other kind of solutions like this. The problem comes when we start to zoom down into the structures. And again, this was mentioned with level of detail, but generally speaking, you get these very low resolution structures. And so for visualization, when you're looking far away, that's totally fine. But when you come to try and measure things, you start to have problems. You won't get very accurate measurements typically from this kind of model. The other thing is, if you were to go inside this building, there's no information. It's just a simple basic object with a textured mesh over the top to make it look like the building. So if we were to go and map the inside of this building with new data, we couldn't just get that data to merge exactly in. So one of the problems with meshes is that meshes are only really focused meshes are only really focused on the surface information. They're not looking at the interior information. And also, it's very hard from a mesh to do incremental updates. So the approach that we take is different. It's a volumetric approach using voxels. And that allows us to map both the outside world, but in this picture here, if you see the building on the right-hand side, at any point we could go inside that building with a scanner, map the interior space, and that data would instantly drop into the model. Also, because we've created the model using voxels, it means we can do incremental updates. So very important, we can add a fourth dimension of time, which is really important to making sure that you don't lose value from a digital twin in the future. So I mentioned voxels, and I'm sure a lot of you have already heard of voxels. A voxel is just a 3D pixel. It's just a cube. They're not new. They've been around for a long time. Minecraft is an example of a voxel rendered world. But we use voxels in a particular configuration called a VOG. And VOGs are really something that came out of robotics that small robots used to use to kind of create maps of rooms, for example. We took that concept, but we applied it to the entire planet. So essentially, we took the Earth and we placed a giant megavoxel over the top of the planet. This megavoxel is then full of multi-resolutional voxels, which pretty much dice the planet into trillions and trillions of cubes of voxels. This is what we call an Earth-centered, Earth-fixed reference frame. So it starts from the center of the planet and works outwards. So it really goes through everything. Wherever you're sat at the moment is actually full of these virtual voxels. It goes through all the buildings, through the Earth's surface, through the oceans as well. Each of the voxels has a permanent position in space and a unique address, a machine address. But to start with, the model is blank. There's no data in it. It's just a 3D georeferencing system. So what we do is we validate the occupancy status of the voxel. Basically, is it free space or is there something in there? So we do this using LiDAR. If the laser beam from the LiDAR passes through a voxel and it's not reflected off anything, then this is free space. But the moment it hits a surface and it's reflected, we label this as occupied. So in effect, what we're doing is etching out the matter of the planet. But at the core, this is a global spatial database for all of this data. It's designed to handle planetary scale data, so thousands of petabytes, and provide real-time persistent access as well. But in addition to that, the use of a VOG actually comes with some other benefits. So firstly, by definition, all voxels are 3D measurement units. So it's very easy to perform calculations in 3D on objects. Secondly, on the surface of the voxels, you can put additional layers of information. Typically, this is camera data, so RGB values, but it can be things like hyperspectral imagery. It can even be radar. So with voxels, you have an aspect of the shape. With the surface information, you've got an aspect of color. And that's where we then apply AI. So we apply machine learning techniques which look at these collection of voxels truly in 3D and understand and recognize what they are and measure them. But in the model, it doesn't just have to work in 3D. You see, every voxel in the model has an infinite number of time states. So you get this temporal data component. So the AI can recognize what's currently there, but also look over historic data and recognize features and compare and contrast. So that gives you the ability to do very powerful change detection. So when you link this together then with the global model, the global spatial database for all of the data, the permanent addressing, the ability to intelligently search, it becomes a really powerful platform for digital twins. So I just want to show you what this looks like. This isn't just a science project, we're actively collecting. So this is data that we've collected using aerial LiDAR. This is above San Francisco. I'm very happy to give you guys access to this, so you can see. This is pretty dense data as well. We're talking about 200 points per square meter in terms of collection. But we take that data, we put it into the voxel model. We also combine it with street level collection as well. So these are vehicles with LiDAR sensors and cameras, which are driving around cities and capturing all of this data. This can drop into the model. But in addition to that, interior data as well. So we have teams of people with backpacks, with LiDARs and cameras that are actually going into buildings and scanning the inside of the building. So in one complete model, you can go from the outside world highly accurately, one-to-one model with 1 centimeter resolution, all the way through into internal structures, even subterranean structures as well that we've started to model. And I mentioned there's a fourth dimension of time. So you have the ability, if we've collected data, obviously over multiple time segments, to use a time view as well. So you get to select the time slice to actually have a look at a city. So as you're building a digital twin, this gives you longevity. It doesn't become outdated. You can compare and contrast the collections that you've done now to collections that you'll do in the future. And again, this is very important for smart cities and digital twins for detecting change. Now, integrated into all of this, I mentioned, is AI, and I want to show you what that looks like. So this is for San Francisco again. These are voxels. It's just the occupancy. And then what we do is we layer on the surface information, the colors. And at this point, this is where the machines take over. So the AI, all these colors here, that's the AI recognizing features automatically and then vectorizing that data. So now you have complete control and flexibility. You can remove things you're not interested in or export them into different data formats or connect them via APIs. The current platform recognizes about 100 different objects in cities, and we're constantly adding to that. Plus, we provide tools for companies to go out and organizations to go and train their own networks to recognize features as well. Now, all of the examples I've shown you thus far have really been in cities, but it isn't just cities. So I want to show you something that we've done with the Earth Archive. The Earth Archive is a non-profit organization with a mandate for really doing aerial LiDAR maps, high-resolution aerial LiDAR maps of forests and jungles around the world. And so this is a scan that we helped conduct in Muir Woods. This is just over the Golden Gate Bridge, and it's a redwood forest. So we took that data, we voxelized the entire data, applied the AI, we're able to remove the trees and reconstruct the ground plane and the surface models, but put the trees back and actually catalog every single tree, recreate the trunks so we know where they are, and know the height and the dimensions of it as well. So we can do very accurate carbon accounting methods and things like forest fire management as well. This has been, profound. What normally would have taken manually years to do was just done in a couple of weeks. And so again, the concept of being able to have a digital twin that can really host data at scale anywhere, and then applying machine learning to it becomes a very powerful solution. So I'd love to answer any questions that you might have, and please feel free to reach out to me or the organization anytime. Thank you very much.
Thank you, Peter, for this interesting talk and perspective on voxels as an approach to digital twins. With this, we have finished the talks from our 5 speakers. I now welcome all our speakers to be back on the virtual stage. Please turn on your cameras and unmute your microphones and join the panel. First, we'll review any question before us that are directed at you. Next, I'll have some set of questions as well, taking up from various speakers that are coming up. So we'll wait for a minute to get questions into the chat. And the first question I have for the panelists is that to bring everybody at par, how do we differentiate the regular geospatial projects and the digital twin projects? When you speak to your customers or when you speak to the community, how do you define that? Because for example, I'll take it to Nicholas first, because ESA has been doing a lot of data creation and data distribution for so long. Similarly, many other businesses, but now we have started calling them as digital twin projects. So how do we, Nicholas and others, differentiate the historic or the current projects from the spatial digital twin projects?
Yeah, good question. I think there's different angles that one can take in order to differentiate a bit. First of all, I think it's still valuable to think about the different natures of digital twins that we are still looking at. On one extreme end, there's something that I would call a product or production digital twin. I think that's a phrase that is used in industry. Whereas most of the digital twins that we are concerned about, or the aspects of digital twin that we are concerned about, are really about natural processes. So there's a spectrum, a continuum between something that is man-made and engineered and the natural world, and the underlying models that are determining the behavior. Of course, these things are not self-standing. There's strong interaction between these components, and I think the digital twins that are relating to city management, urban evolution, are a good example where these various categories meet. Another way to look at digital twins is for us, in Earth observation, it's really the prognostic potential that we are trying to unravel. So when we try to differentiate what we have been doing in the past, we said Meteorology and climate research was already predicting and using models heavily, not so much other observational categories. And that's now the full expansion of these principles into all domains of Earth observation. And that by implication also means completely new types of measurements and data that's being integrated. So that's a bit how we tackle this.
Thank you. Thank you, Nicholas. That brings a lot of clarity. Anybody else want to take on this question?
If you allow me, Nick did a great job in explaining it and giving the samples. And from my perspective and what we've learned is actually we do have not one digital twin, as Nicholas already pointed out. So the digital twin is driven by use cases and the expected outcome. So we have multiple digital twins even for the same space. And the second, which I want to enhance Nicholas' statement, is basically we do have different dimensions of digital twins. So what we were presenting primarily was the static dimension. In terms of urban digital twins, we call it also a 3D city model, if you like. So nothing really so special. But we also have a dynamic dimension when we bring the sensors into this game. So and simulations, obviously. And then we do have a third dimension, which we should not underestimate, and that's the social dimension. Because within a city, humans are living and we need to respect their needs, their demands, their behavior as well, when we talk about complete and complex digital twins. So we need to think about all these different dimensions as well as the different use cases in order to make something good out of it, which really helps and brings the society forward.
Thank you, Dr. Jashnok. Yeah, please.
Yeah, Uwe, no, great points as well. I think really when we look at digital twins, we've gone through a number of iterations. The first generation were pretty much 2D kind of representations of systems with some data going in, and then digital twins was all about having 3D data, and so we built 3D data, and it's great for a visualization part, and then it just starts to get outdated. And I think really what we're starting to see now is the fact that you can't view a digital twin in isolation. Right? It's not just about these relative reference frames which don't relate to each other. So when you're really starting to look at cities, you have to join it all together. And there's a wealth of data, not just the data, for example, that we collect or our partners collect, but many feeds of data that can come in and really enrich it. And so it's about really kind of creating that environment that would facilitate all of this data coming in to provide different insights as well. So I really feel we're now on the stage where digital twins are starting to become much more useful than kind of the early stage digital twins that we used to have.
Anybody else would want to tackle as well on this, or can I move to the next question? So the next question is again an open question. So are we seeing more of a tech push from the sector to the user side, or for the AI and digital twin offerings, or are also users demanding more for AI integration into digital twins?
So I could offer a response there. So I think it comes back to the use cases, and what we've seen with our work is that you've got to really be careful to get to the bottom of what's actually needed, and we made the distinction between just the visual value versus the analytical value of the models. But not that obvious. You have to really drill down and get down to what the user really needs. And in the case of a true digital twin, where you'd have your live inputs and other feeds, you'd get to a situation where the visual may not be that important. But people tend to focus on the visual. That's the first thing they want. You show them they want it. And you've got to drill deeper and get down to the actual use cases, which I think is normal practice now, but that's essential to get it off to a good start. Else it'll just be a pretty looking picture.
Yeah, the great point, Chris. I think I would also add that particularly in the geospatial industry, sometimes we're quite stuck in our ways. And so we still view geodata as kind of layers on top of a map. Back from the days when we literally used to draw layers on top of maps physically, that's how we think about it. But we have a new opportunity here really with the future of digital twins, which is to really index them in the same way as Google indexes textual data on the web. And that means we can start asking it questions. We can ask it, how many street lights are there in San Francisco? What's the tallest tree in your woods? Where is the vegetation overgrowth? The interface into this data is all going to be driven by AI, and it should be driven. And I think we've got to start looking at those kind of technologies to put more of a human way to interact with the data than maybe some of the traditional things that we kind of grew up with in the geospatial industry.
If I make a quick point on this, I think what is probably helping this whole process is the realization that if we integrate additional types of data, I think a lot of the applications will emerge that are not visible by purely what I would call, in the broader sense, imaging data. I mean, most of the examples that we have looked at is imaging, but think about temperature, think about gravitational chemical data. All of this is available and can be generated on the scales that are relevant here. Yeah. So the complexity of the data space is something that has been only scratched on the surface, is my feeling. And being smart on integrating this into the concept, and as been said, not to focus exclusively on the visualization. That's only the first step, I think, is probably helpful. So I concur with everything that's been said so far.
Yeah, I'll now go to individual speakers and on your points and ask few questions. I'll go in the order of the speakers. So again, for Nicholas, how is ESA planning to present these digital twins to policymakers and public? That's one question. Second question is, do we have the tech capabilities to actually release these digital twins onto the web so that people can start using from their browsers, or are you looking at special tech capabilities to be enabled? And a third question is, how do we make digital twins more open and accessible, and also those models more open and accessible? Yeah.
So with regards to the concrete implementation, I gave the example of the initiative called Destination Earth, which is in implementation as we speak. We are in the first year of realizing this system, which in the first phase is targeted to address specific needs of the European Union. So for this first stage, we are obliged to deliver models and digital twin system functionalities to the European Commission to address specific things that they need for their various directorates, for their specific services, in order to address these things. And this will happen over the next 2 years. So in a gradual approach, we're implementing this, and first results are already being used, but it's a rather closed system. The moment when this whole system really opens up is the subsequent phases. And of course, I tried to give you a bit of a feeling that from a Earth observation and European Space Agency perspective, we really want to bring in all our Earth observation data. And again, this is a multi-dimensional data space. Wind speed data, atmospheric pollution data, all of this is available. And we want to use the most advanced models in order to bring this into an open ecosystem in which anyone can contribute to this. The general data policy on Earth observation data with the European Space Agency and Copernicus European Union data is free and open. So we are talking about free and open data anyway, which is facilitating the entry into this open system that you're looking for. To put it in other words, we see digital twin as one key implementation in the interaction with the users and non-expert users in particular that has the highest potential to fulfill the ambitions of openness in every respect. We're not talking about open software here. We are really talking about the open value chain from data acquisition to the final information management aspects. And that's new. And I think we share this vision with a lot of colleagues, and I see a lot of things converging in that spirit. So I hope that helps.
Thank you. Thank you. I'll now go to Dr. Jasnak. I really like how you presented, defined digital twins, saying that more than a pretty picture, we need insights. I think that's how you tried to summarize digital twins. From Hexagon perspective, at this point in time, what is the model of delivering AI capabilities into digital twins? Are they case-to-case basis, or is Hexagon providing these models and capabilities into your software so that professionals can start using that? What is the approach of Hexagon in this area?
Thank you very much for the question. I nearly forgot to unmute myself. And prior answering that question you stated to me, maybe I'm going to pick up one question you stated to Niklas. So all videos you've seen was basically screen capturing from browser implementations. So all these videos were run in the browser, so that's the easiest and the fastest ways to disseminate it to public within the organization, so it should work. Now, for the question you state, of course, we do have similar, like the colleague of Omar presented, we also have a kind of implementation which is embedded in our software platforms and portfolios, of course. We are both commercial software providers, so it would be stupid not to do this. Of course, everyone has its own flavor, which is fine and fair. However, we do also have production lines, as I said. One of the key is really to reach a high degree of automation. And in order to reach this high degree of automation, and also with good results, we need to respect that you need to specifically train networks for specific sensors. Not every sensor has the same capabilities, especially when it comes to LiDAR sensors. So you need to adapt and fine-tune and retrain networks. And we at Hexagon, especially with our friends from Hexagon Content Program, have a complete suite specifically trained, so that basically the whole process from landing the plane, taking out the data, till you have a 3D super mesh model, maybe fused with the city side model, as I've shown for Munich. So these processes are highly automated and specifically adapted to our sensors, as well as a lot of these object detections in LiDARs are specifically trained, of course, to our sensors first, but obviously open also to other sensors. And I think that's one piece of the story of AI, which you typically don't see because you're not interested in. You know, at the end, our customers, for the static part, you know, if I'm going to be very generous with my statement, I would say they don't care if you're going to make it hand painting or with AI. At the end, they need the model, which sets the frame. Of course, we have a high interest in making it on AI, because otherwise we cannot cope with a vast amount of data. And when I have a chance to look for one question, and may I answer one question which came from the chat concerning standardization. It's a very tricky question, a very interesting question. I think we should focus on standardizing the objects and the ontology between the objects, and not the process of how to create these objects, because here we do have the freedom of having competition in the algorithms, having competition in different networks, and see what's the best of breed to generate these objects. But the objects and the ontology on the objects, this is something we should think about standardizing. My 2 cents on that one.
Sure. Omar, what's your view on the point that Dr. Ujashnuk has just said?
Yeah, absolutely. Yeah. I think the need for standardization is critical. Here's the thing. I think it's important, but at the same time, it's a bit of a challenge. In the world of, let's say, deep learning models, for many of the scenarios that we've shown today, it's a little challenging to have like one model that conquers them all, right? Like you can have a model that works fine in some geography, like the US, for example, but when you apply it in, you know, another country, it's not performing nicely, right? And that's why I think we should be having those, you know, kind of global models that are trained on global data from different geographies and are performing nicely. But at the same time, I think there's going to be need for geography-related tailored models, right? And that's not only for 2D, but for 3D as well, right? And I think maintaining a publicly available repo of those models and make it accessible to the community and enabling sharing back, right? So people can take these models, tweak it, and upload it. I think enabling that sharing mechanism and collaboration is more important than standardization, in my opinion, because trying to achieve standardization is going to be a little tricky. because data sets differ, geographies differ, everyone has different requirements. You see where I'm going? So I would vote more for more collaboration / openness versus standardization in that case. But I think eventually it can achieve pretty much the same goal.
Thank you, Omar. And Peter, your 2 cents on this?
Yeah, no, I agree both with Omar and Uwe on this. I think that when it comes to the AI, I agree that it's very hard to standardize. And in fact, I don't think you really can standardize, and you wouldn't want to anyway. You need that kind of creativity. You also need to be testing new models, which will be very different to each other to see the effectiveness. But I do think we can standardize on the data formats. So the ingestion formats, the interconnects between systems. I think that's very interesting. Definitely organizations like OGC have started a lot of this as well. And so supporting some of these open data models can be very interesting. So look, any of the companies that are here, we can't map the whole world out ourselves, right? It really is a huge team effort. I think, I can't remember the presentation, but there was a slide about that. And so the ability to access all of this data that's being generated by everybody in a way is very important. So I think some standardization around the data itself, the data models, would be very welcome.
Thank you. I think that partially answers or fully answers Marco's question. And then we have another question coming again is how to integrate building information models into the systems. Are there common ways in understanding existing data? I'm myself not very clear on how the question is framed around. If anybody is able to understand that question, we can answer, or we can. I'll ask Marcus to make it more descriptive or more clear. And then before that, we'll move to the next question from Patrick, where he says he's coming from a perspective from the South African mining sector, which is moving towards smart mining. And they would like to find out ways in which AI models can be used for risk profiling in underground environments in areas such as deep gold mines. So any particular examples or use cases that anybody of you have seen from underground mining, or you want to point out, Patrick, towards those resources? You're welcome.
Harsha, I would just give a short answer to the question of Marcus with the integration of BIM models. It's a tricky topic, actually. So the technology is very simple. You need to make sure that the scale is right, and then you place it. Now, the really tricky part of BIM with the integrating in a digital twin from an existing frame in an existing city is really finding the right orientation. Because a BIM model itself is oriented internally very well. Fully described, everything is fine, but we have no idea which side points to north, west, south, or east, and this makes it tough. So we made a digital twin for the Swiss rail with ticket machines, and we had virtually no clue on what's the orientation of the ticket machine. So we know that we don't place it upside down, but we had no idea. So we make kind of distance function to make a best guess, but that was it. So I guess. BIM it's good to integrate. It's nice because it describes the future and also describes interior very often, as Peter already showed. But really, at least a very trivial obstacle we found is really the orientation in the outside model.
Yeah, maybe just to answer that, great point, Uwe. And this is kind of what I was touching on a little bit before when I said about when people build digital twins with relative reference frames, they're missing a trick, right? If they can use a global frame of reference, then it becomes much easier to locate, and to merge with data as well. So within the Voxel approach that we take, it's multi-resolutional. So we can take many different types of data in. We can take BIM models in there as well. But we have to use a lot of techniques, to align it, like SLAM techniques to align it within the actual structure as well. So I think even if you are collecting in a relative frame and it's just a digital twin that doesn't really need to interact with anything else, if you do have the ability to really properly georeference it, that data becomes much more valuable and easier to interoperate between different systems and different data sets.
Sure. Thank you for answering Marcus' question. I'll go back again to Patrick's question, probably to Chris or Omar or anybody else, even taking examples from underground utilities per se. Do we see automation in AI being done in, for example, let's say underground utilities and also in mining sector, underground mining sector? Chris, Omar, anybody want to answer?
I haven't particularly worked in that specific scenario, but I think the idea is like the same foundational idea that we've been talking about, right? If there is anything from a visual perspective that a human can detect under 1 or 2 seconds, if you can look at that picture or that 3D model or whatever and define that, hey, this is risk or whatever, there is a space to automate that through deep learning, right? Like you can label data, you can train a model and do that. Now, what I envision is that on its own, it's not going to be enough. It's going to need to be combined with geospatial analytics. So I've seen the pattern of, like detecting different things that could be proxy to understand risk, but then bringing, things like elevation and, dimensions and stuff like that on the top of the deep learning results so that you can derive a risk score or something like that. I think that's, a general way of approaching these kind of problems.
Thank you. Yeah, one more. Yeah, sure, please.
One more element which pops up into my mind in what Omar already said is I'm thinking here more like on maybe not on AI, but on any kind of machine learning. So as it is in a deep mine, so scratching the surface is not really helpful, typically not. And also all these mining operations would most probably don't result in surface movement where we do have technology to monitor those. So I would guess that the best thing, or my best guess would be that you're going to apply some machine learning, some algorithms on different kind of geo-monitoring sensors where you're going to see trends on shifts and these things. But this is not necessarily in terms of visualization, as also Nicholas pointed out earlier. So not everything needs to have a visual representative. So here I would more go most probably in the direction of sensor monitoring and estimations and predictive analytics on what does this specific behavior means for the mining operation. So this was something which popped up in my mind while Omar was speaking about.
Yeah, and also believe Hexagon has specific solutions for this mining sector and monitoring sector from the monitoring perspective, where we can bring in different perspectives to create predictive and prescriptive models, right?
Yes, we do, but I don't want to make a sales pitch on these things. So I just was more like general spoken that.
Yeah, so probably Patrick can reach you to understand more about that. I'll help you both connect. Thank you. I'll now move to the question while we wait for some more questions. I'll now move to Chris, where he spoke about the leader analytics solution from them. So Chris, are you currently using these solutions as part of your internal workflows, or are you also offering this as a turnkey solution to other partners?
No, it's the LiDAR-netics is very much one of our internal processes, and we've developed it because of the huge number of projects that we do and the huge challenge and overheads in processing the big data sets. So it's still fairly new, but having said that, the state it's in, it's very robust. It's being used every day on big projects and giving good results. We have some of the projects which have very fast turnaround times, for example, 12-hour turnaround times for some of the projects. And there it's just been invaluable. So it will continue to evolve. It's probably quite a novel application because the machine learning and the AI is now on the LiDAR and not on the imagery. And that's got its own challenges. It's quite multi-dimensional. Of course, it's three-dimensional to start with, but there's other factors, intensities and number of returns and other things that have to come into it. So no, very much internally, and but the benefit will come out in the product and the service.
Sure, thank you. Then the question to Omar is, Omar, you've spoke about the availability of pre-trained models. How is the uptake of this offering from ESRI in the community, and what are some of the most sought out models from the whole suite of models that you're offering?
The uptake is massive, to be honest. Like, some of those models have been downloaded for literally tens of thousands of times so far, with the most famous being the building footprints, land cover mapping, road extraction, definitely. Building footprints still for different geographies because we have multiple models for that. And then we have the power line extraction, I believe, from LiDAR, because a lot of utilities need that. I think those would be the ones that, you know, I would think immediately on top of my mind. But I think the kind of adoption has been like really insane because it's really plug and play. I know that sounds a little salesy here, but I definitely encourage like my peers today and, you know, the rest of the community to encourage that idea of pre-trained models and make them available, because I think this is the most significant barrier to entry that I've seen today, right? Like, a lot of the analysts who want to use those models are not necessarily deep learning experts. So if we put those pre-trained models and, you know, we share insights about the kind of data they've been trained against, their accuracies, how to use them, etc., make them more accessible, I think that's going to be a turning point.
Sure. And the next question is to Peter, is that my question is, what actually ticked you to create this Voxel technology, and how will this technology be complementary to the existing tech stack, which is already available from various other providers in the industry?
Yeah, really good question. So I view this in a little bit of a different way. I think, you know, there's a big macro trend that the world is moving to 3D compute in a very big way. And there's two sides of that. There's the virtual world, which is what we hear about a lot, the, you know, metaverse and omniverse and Epic and all the games engines, right? And then you've got reality capture. And reality capture is really being driven by an explosion of LiDAR sensors that are reducing in cost, so kind of creating all of this amazing LiDAR data. Now, in the virtual world, there's lots of big platforms that are really scalable to handle that. When you look at reality capture, there aren't. They're really poor applications, generally speaking, desktop or single server, not utilizing multiple GPUs, clustering across clouds. So, you know, you need to build something that can really scale to handle planetary, you know, level data. And so when we were looking at that, you've really got three options, you know, for reality capture. You either keep it as points, and points can be great, you know, they're unstructured data, but, you know, they can be very accurate, but there's a ton of processing that you have to do, and it's very hard to manage those. And so most companies do the processing and then archive the points off and never touch them again. Or you can go through to meshes, and meshes are great for visualization, much lighter weight, but you lose a lot of the measurability and the ability to update there as well. And so voxels kind of sit in between. A VOG, not just a voxel, sits in between those two data sets. So it's a structured data set that you can keep the data persistent and do analytics on, but at any point you can convert to a mesh, or you can go from a voxel back to points as well. So it just kind of increases the longevity of the data and gives you more flexibility to use it. And we saw this a lot with the robotics industry that was really using this approach. And we really kind of took that from robotics and brought it to geospatial. So that's the reason why.
Sure, thank you. Marco has a comment for any of you to look into it. It's available in the chat window. He's providing a clarification. So I think we will close in 5 more minutes. I have a few more questions. I will come to Nicholas and try to understand about the ESA projects and what is the role of the commercial sector, because you've seen a lot of capabilities in the commercial sector, like how it's from ESRI, Hexagon, all these people are talking here. What kind of collaborations are you already doing, and where do you think the industry needs to invest, because ultimately for this ESA's grand vision to be achieved?
Yes, there's again a different dimension, but let me first stress that ESA, the European Space Agency, is a procurement agency. So whether it's satellites, whether it's ground segments, whether it's data management activities, we are relying on industry to provide the services, the functionalities to do all these things. So it's not a ESA proprietary solution that we are looking for. 85% of the budget that our member states are giving to ESA is going directly back to the member states and to the industries. For the specific case of the digital twins, I see 2 ways for industry to engage. First of all, we build up certain instances, specific services that we would like to hand over to operational service providers. So there's that possibility. But of course, the development of the system, the validation of the system in itself constitutes a industrial procurement. So becoming a supplier to the system, to the system is another option. And there's a final option, of course, on the technology side, because we are also an R&D agency. We are always interested in partnerships and interactions with industry directly in order to foster the research and development aspects and the scientific basis for what we are trying to do. So I think these are the three main levels of interactions that we see. And again, the European Space Agency doesn't have any sense, or doesn't make any sense without industry.
Thank you, Nicholas. I have two questions. One on trust. One is that because we are now talking about a lot of pre-trained models being available to the community to use, and the community is using it. How is the trust on those models, and how is the feedback loop happening, and how are we improving these models? So anybody wants to take this and answer it?
Harsha, can you repeat the question again? Sorry.
Yeah, so I'm saying, like, now we see a lot of pre-trained models available, right? So how is the trust on using these models, and how is the feedback loop from the users on the outputs of these models and the outcomes of these models, and how is this feedback loop being closed and improving the models?
I can reflect real quick on both. So from a trust perspective, it really depends on what do we mean by trust, right? I think if we mean, for example, confidence in the results.
Yes, confidence in the results. Yeah.
Awesome. So I think this is going to be a case by case, right? Like, for example, we are seeing customers, like, using those models, and they're very satisfied with the results. Others, as I mentioned, they apply it, they see it performing nicely in some areas, some other areas it's not. Which brings us to the second point, which is the feedback loop, very important. What the kind of pattern we see prevailing is taking those models and then retraining them using local data, especially for areas where the model is not performing nicely, right? So let's say you have that city, and then for the northern part, for example, the model is not performing nicely. So you go on and label some data and then retrain the model, and then the model will apply something called transfer learning, which is the idea of avoiding the training from scratch, but just fine-tuning the model to be smarter. And then the model would generally perform nicer at these areas, and so forth. We see that pattern happening a lot, and we actually encourage it, right? Because we know that it's very hard to have that is perfect in all contexts, but then we encourage that idea of transfer learning, especially if it's done easily, to train with local data. That's the kind of the major feedback loop that I see happening. I think if there is a way to ingest more feedback from more users, to feed the global model again, I think that would be fantastic. But we don't have that yet. I think it would be a great idea. And it could be a form of, like, federated learning, which is, I think, being applied by many companies like Google, for example, where they try to teach the models or make the models, their models learn from the kind of interaction that users do on their different phones, right? Obviously in a totally anonymized fashion, etc. But the major feedback, path that I've seen so far is that idea of fine-tuning models with local data.
I think one element, in addition to what Omar said, and I fully agree with that, you need to also be very open with the results. So you need to provide not only, so to say, the sketch of the land use or these things. You need also to provide the probability map, so you can identify what's the probability of a certain identified object. So you can really see what is false positive, what is false negative, and these things. So just getting the result alone is maybe not enough. So you need more information that a user which wants to analyze and creates this trustness has a chance to dig in and make a kind of assessment of why the AI thinks something is like that. And it's very helpful, and that's needed. And we have executed dozens of different samples where, for example, a sun shield, a sun cover on a building was wrongly identified as a roof. And actually, only with the help of the height information, you can really grant if it's now part of the roof or if it's part of the the terrace and covering the terrace and with sun protection. So these kind of information is helpful in order to create this trust in this relationship, and the ability, as Omar pointed out, of retrain models according to my specifics is also a helpful topic in there.
Sure. There is one more question. Last question we'll take from Marco is that we have spoken about the vision of having micro twins, macro twins, and all these kinds of twins being integrated, like how we see the spatial data getting integrated at various scales. Where do we, what are the key challenges he's asking about federating these digital twins, example, local or local to global kind of a scenario?
It's a great question. And I think just, sorry, to add to that, the market's not doing that at the moment. And I think it's something that we need to start thinking, about. I still think, a lot of the market is just thinking about digital twins plural as these relative frames, of reference, just solving some kind of narrow use case. And I don't see yet, the industry, with the exception of, the very big projects, obviously, like, ESA's doing in terms of the entire digital twin of the Earth. But when you're coming into things like BIM, for example, or even city modeling, or modeling for autonomous vehicles, very often these are just separate silos. So I think there's great value in working out how an industry can come together and really put a structure to share that. So that's definitely something we would welcome.
So I could just add to that. You can't ignore the whole governance aspect. And there are models around this, and federation, of course, is one of the aspects of good governance. So without that, you end up not really making it suitable for the organization and for, ultimate consumption. So governance models come on top of all of this that we've discussed.
My 2 cents on that would be, as I said, or as I tried to point it out, at the moment we are on the stage that digital twins are use case driven. And we need to be very carefully that we do not fall in the same trap as we had with geospatial. So when we do data acquisition, we're going to acquire data for a specific purpose. And whenever you're going to move this purpose away, this data may not fit anymore. And the same is with federated twins. We have to be very careful in bringing digital twin data together, where the purpose of the creation of the digital twin is not matching to each other. And then we're going to create results without any meaningful element. So it's a point of, as Chris pointed out, the governance is a highly important part in order to make this fusion of different digital twins a meaningful activity.
Thank you. Very valuable feedback from all of you. So this fantastic session, all those who supported this event and are with us today as speakers and as the audience, IT will make this session recording available. Please feel free to recording in your network. On the session page, the presentations are also available. When you answer questions, you get them answered via emails. Goodbye, everyone. See you in the networking session.
Thanks, everyone.
Thanks, everyone. Have a good day.
Thank you all. Bye-bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the satisfaction survey, connect with interesting profiles, or speak one-on-one using the chat and video function. After the 30-minute networking session, we invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits and poster boards, and build your personalized AI for Good program. It was a pleasure learning with you today. See you at the next AI for Good.